Hi everyone. In lesson 14, we're going to calculate conditional probabilities. We're going to see when we divide probabilities and how we update probabilities, the Bayesian approach. Now, first of all, let's go back to the idea of a conditional probability. So in example 1 down here, what is the probability that a randomly drawn card is the 3 of hearts, given that, or conditioned on the fact that we know that the card is a 3? In other words, what is the probability of getting a 3 of hearts given that the card is a 3? So let's say that you draw a card from a deck. You don't look at it, but I do. And we ask, what's the probability that this card is the 3 of hearts? Now let's say that I tell you, hey, I see your card and I can tell you right now that the card is a 3. The rank of the card is 3. What is the probability then, the updated probability, that you have the 3 of hearts? Because here's the idea. The prior probability of getting the 3 of hearts was what? Well, how many cards are there in a standard deck without the jokers? 52 cards, each of them equally likely, presumably. So the probability that the one card you get is the 3 of hearts will be 1 over 52. That's the prior probability. But now I'm looking at your card and I'm telling you, hey, I'm telling you that the rank of the card is a 3, which means that we're restricted to this row over here. What then is the updated probability, the conditional probability, that you have the 3 of hearts, given that you know the card is a 3? Assume I'm being honest. It's going to be, well, how many of these cards are the 3 of hearts? 1 card. How many cards are 3s? 4. So the probability, the updated probability, is going to be 1 over 4. Again, I'm taking the Bayesian approach, this idea of updating probabilities. The updated probability conditioned on or given that the card is a 3 is 1/4. I'll put this in red. Because before, we had a pool of 52 cards that this card could have come from. If I'm telling you the card is a 3, we're now down to these 4 cards, and only one of them is the 3 of hearts. So instead of 1 over 52, it's now 1 over 4. All right, that's the idea of conditional probability. Now, what are some formulas we can use for conditional probability? Well, remember, before, when we talk about the probability of getting A and B, this was the general multiplication rule for these AND probabilities. The probability of getting, let's say, an ace first and a king second, remember those card problems? The probability of getting an ace first and a king second, this was equal to the probability of getting an ace first. Very conveniently, that corresponds to event A over here, times the probability of getting a king second, given that, or conditioned on the fact that we got an ace first. We're building up the scenario. The probability of A and B equals the probability of A times the probability of B given A. Now let's say that we solve this formula for this conditional probability, P of B given A. We can do that by dividing both sides by P of A. We do that over here. P of B given A equals P of A and B divided by P of A. And remember, this only makes sense if P of A is non-zero. We're assuming that P of A is not 0. Which makes sense because we wouldn't want to condition on an event that was impossible. Now, bear in mind, in graduate level probability, in continuous probability, you do this when studying Brownian motion, but that's more of a calculus idea. For right now, we're assuming that P of A is not 0, that we're conditioning on a possible event. If you turn it around, it looks like this. The probability of B given A equals the probability of both events happening over the probability of the event that we're conditioning on happening. So if you look at this in terms of a frequency table, like in the tutoring example, or if you want to think in terms of dice or cards, you can think in terms of ELOs, equally likely outcomes. The probability of B given A equals the number of trials or ELOs where A and B both happen over the number of trials or ELOs where A happens. So instead of thinking in terms of fractions or decimals here or here, we can think in terms of integers on the top and the bottom. That's more convenient. And by the way, why does this make sense using a Venn diagram? So imagine that these are all possible outcomes. Let's say we're talking about equally likely outcomes. Okay. So here is S, the sample space for all equally likely outcomes. S is all of this. So let's say that this is event A. In here are all the ELOs for which A occurs. This is event B. This is the event B, and in here we have all the trials for which B occurs. And let's say that there is an overlap, an intersection here that's not empty. This in here would be A and B, the intersection. This inside here would be A and B, the intersection, the overlap. So what is the probability of B happening given that A has already happened, let's say, given that the ace has come as the first card, for example? Now, we're assuming that A has already happened. So we're focusing our attention on this purple disk over here. We're assuming that A has happened. A has happened. It's the event we're conditioning on. A has happened. For example, the first card coming up is an ace. A has happened. Given that A has happened, what is the conditional probability that B will also happen? Well, if B is also going to happen, that means that both A and B will have happened. So we're basically asking, when you look at this overlap here in green, and if you think of probabilities corresponding to proportions of the area in here, we're going to talk about that idea later, relating probabilities and areas or proportions of areas. Here's the deal. We're going to be asking, what proportion of the purple disk, what proportion of this area in here does the green area make up? So for example, if this green area makes up a third of this purple area total, then the conditional probability is 1/3. We don't care at all about what happens out here. We don't care at all about what happens out here because remember, we're assuming that A has happened. As far as we're concerned, our world is now restricted to this purple disk. We're now asking, what proportion of this purple disk does the green overlap make up? If the green overlap makes up, say, a third of this purple disk in here, then the conditional probability is 1/3. Okay, so pictorially, that's why this makes sense. The new world is P of A. The probability of the overlap over the probability of this new world, right, the A, that's the conditional probability.